So we are starting again now, the last session of the day. So we have the pleasure to have Christoph Lampert, and he's going to talk about incremental classifier and representation learning. Christoph.
Thank you. Hello? Is this on? Okay. Yes, welcome to my talk. My name is Christoph Lampert. I come to you from IST Austria. IST is a young research institute close to Vienna that you might not have heard of, but that you should remember the name now. And just to start very shamelessly, we are hiring at the moment. We have graduate school positions, we have postdoc positions, we have excellent faculty positions. So if you want to move out of the US, come to a more stable country, Austria is a great location. Okay, so closer to the mic. Like that? Oh, then I don't see my own slides anymore. Like that? Okay. So in my group, which is about computer vision and machine learning, we have a big goal, as many people in computer vision. It's a very modest goal of building automatic systems that learn and act autonomously. And by that, I mean, we're aiming for more of the right-hand side, not the left-hand side. And this is a goal that many people share in the community, and of course, we're very far from achieving it. So what we do is we kind of settle for a more modest goal that would be, can we at least build automatic systems that analyze and interpret data? Like, since this is a computer vision session, let's look at this example of an image, and maybe the computer should be able these days to build some kind of internal representation of that there's three people sitting there, that they're drinking, that one of them is telling a joke, something which to a human, of course, is very natural to get directly from the image, where unfortunately the computer, despite all the recent progress, is not at that level yet. So whenever a problem is too hard, what do scientists do? We break it into smaller parts. So what we really work on these days in computer vision would be individual, well-defined tasks like classifying a scene, if an image is indoor or outdoor. Action classification is somebody jumping or drinking, and so on. And this is just meant as a lead-in to say that a lot of things that we do at the moment can be broken down into many individual learning tasks. And a big question is, how can we solve these tasks efficiently and incrementally over time? So the easiest you can think of is, well, let's just try each, if we just draw each task at this kind of abstract bubbles, well, you can solve each task independently, and that way, well, you can solve them one after the other, and maybe your system is done. But clearly, that is not the most efficient way to, when you try to solve a new task, you first forget everything that you have learned about the previous task. So this is not what would happen in a natural system, and it's clearly an inefficient way of learning multiple things. So what instead one should do is maybe consider some kind of multitask where you take all the data from all the tasks you have, you throw it together into one multitask learner, and then you are able to afterwards do better prediction because you made use of shared information, maybe you learned a better representation. So multitask learning is very promising. The only problem is in the context of solving more and more difficult things, multitask learning is kind of stuck in the system where you have to have access to all your data at the same time during training. So what we would be really after is some kind of open-ended, continuously improving learning where, yes, you want to learn multiple things, but you don't want to learn them all jointly, but you want to learn them incrementally, like in this picture where first you learn one thing, then you learn another thing, and in the meantime you have some kind of underlying continuous learning system that gets better and better over time because it has more and more experience. So this is what we call lifelong learning sometimes, and this is the general picture into which the rest of the talk you should see as some kind of context. So we want to build systems that can continuously improve over time by learning more and more things without needing necessarily knowing in advance what will come next. So what exactly I'm going to talk about is a very simple aspect of this kind of lifelong continuous learning, which is only about multi-class learning. And after 5 days at NEPS and 1 day of workshops, you might have seen a lot of deep networks, and you think that everything can be solved by just training a deep network with stochastic gradient descent. So I changed the title for 1 second, and instead of the original title, which is Incremental Class and Representation Learning, I will call it the Exemplars Strike Back, and you will see why. I should say that this is mainly work by my former intern, Sylvester Rebuffi, who's now moved to the University of Oxford, and my student, Alex Kolesnikov, who's still at IST Austria. So what is this exactly about? Well, we want to do multi-class learning. So we want to build a learning system that can learn from, multi-class learning, but in an incremental way, meaning that the data for each class comes in one after the other. First, I see something about one class, then I see another class, the data, then I see another class, the data, and so on. And ultimately, I want to be able to learn about everything, but I cannot just take my data, throw it together, and shuffle it IID. And technically, what we assume is we have a stream of data that comes in, and it comes in some kind of class-ordered fashion. So first one class, then the next class, then the next class. We might be able to process batches of classes at a time, but definitely not all of them. There might not even be an end. It might be an open-ended system. The output that we want to produce is a multi-class classifier. And of course, since the number of classes will grow over time, it should be a multi-class classifier of the classes we've seen so far. And in order to make it more interesting, we impose some conditions. In particular, the computational requirements should stay bounded, and the memory footprint should not grow. And in particular, this rules out that we just store all our training data, and whenever new data come in, we take all the stored training data, throw it together with the new one, and then just train a regular multi-class system based on everything, which would solve the task, but it would not be efficient. So we want to really make use of like incremental steps in the learning procedure. So clearly, this is not a new topic. This has been studied for quite a while, and there is a lot of possibilities how you can address this. So let's fix some notation. I'm going to think about a very typical classification system where you have some kind of feature extraction pipeline followed by some kind of classification step. You can think of this as a deep network where all the starting layers are your feature extractor, following by one classification layer, or you can think of it as a support vector machine with a fixed feature function. Ultimately, we're just going to distinguish between the feature representation, which ends somewhere, and then the very last layer that takes the features and turns it into a sum per class output. So, for example, it could just be the posterior probability of a class given the input. And then we will assume that that the data comes in batches, which we denote by capital X, and then an index S, and that is basically the same as the class. So X1 would be all examples of class 1, X2 would be all examples of class 2, and so on. So how can we train in such an increment with data coming in such an incremental fashion? Well, we all know how to train incrementally already, so we can just do stochastic gradient descent on some multi-class objective. And what will happen is that we will start with a certain number of classes, like I showed here, cats and dogs. And if we have batches of at least 2 classes at a time, we can randomly shuffle within them. And then after we have trained on this kind of data, most likely we found a good classifier that can distinguish between cats and dogs. So everything makes sense at this stage. The problem is what happens when the next batch comes in. So what typically one would say is, well, we have new classes. No, it's trucks and ships in this examples. So these are neither cats nor dogs. So what we should really do is we should assign new labels that are positive for the truck or for the ship, and they will be negative for cat and dog, because clearly they are neither cat nor dog. And now, if you continue training with stochastic gradient descent, you will observe that the quality you will learn decent ship and truck classifiers now, but the quality of the cat and dog classifier will decrease rapidly. Which is a very natural effect, because every example you've seen at this stage or later will be a negative example for all the earlier classes, and then the stochastic gradient will just push the parameters down and down. If you have a biased term, it will go down and down, because the classifier just learns that it will never see a training example of the first classes anymore, so why should it ever even be able to predict these classes? So you can also think of this as taking an existing network and then fine-tuning it on a completely different task. Clearly, it shouldn't remember the old task. It should fine-tune just to specialize on the new data. Right? So this is not a successful strategy if you want to, in the end, get a multi-class classifier over all classes. It will always only fit the latest batch. So how do we fix this? Well, clearly, we want to retain some knowledge about the early classes. And one way to do is we can just not train the classifier for the old classes anymore, because if we do, they would deteriorate, so just let's not train them, right? So what we would do is more of a batch-by-batch situation looking like this, where now we train a new classifier for trucks versus boats without touching the weights of the cat versus dog classifier anymore. Unfortunately, that is also not a great idea. So in particular, now we train on each batch completely separately. There's no exchange of information. So there's no guarantee that the classifiers we learn in the first and in the last stage know about each other. So the classes of the first and the last batch are never separated in any way. So we have a good cat versus dog classifier. We have a good boat versus truck classifier. But when you evaluate it on a new data point, it might have an arbitrary, outcome on the intersection of both. Actually, it's even worse. So if we think about not just learning this classification layer, but we also learn the representation layer, which is what we do in deep learning, right? Then it's not even just enough to fix the old weight parameters. Because when you look at what is the output of these networks typically, you have some kind of inner product between feature vector and weight vector there. And if your feature vector changes arbitrarily, but the weight vector is not changing anymore, then the results will still deteriorate, even if we never change the W vector anymore. And this is a very classical effect, sometimes called catastrophic forgetting or catastrophic interference, saying that if you continue learning the representation, then the quality on the old classes will get worse and worse. And this is also a phenomenon that, it happens in these systems, but it's not something we would expect from a natural system, for example. That would be like you have a kid, it goes to the zoo, it learns about new classes. When it comes home, it has forgotten about its siblings and its pets and so on, right? Because it just learned the new classes and, right? That would be very disturbing. So can we do something against catastrophic forgetting? Catastrophic forgetting is not, it has been observed a long time ago. There has been some proposals to choose a specific activation function or do some regularization, but I would not consider this a solved problem at all. So what alternatives do we have? One thing that works remarkably well in these kind of situations of incremental class learning is the so-called nearest class mean classifier, which was in this form proposed by Thomas Mensink. And that goes away from this weight vector type of linear hyperplane classification, and it does distance-based classification. So it's a very simple system. So whenever for all classes that you observe, you compute a prototype, and this prototype type is just the average feature vector of the class over all examples that are in the training set. And then if you want to classify, you don't compute some inner product, but you compute the distance of the feature vector of your new example. So that's phi of x is the example you want to classify. You compare it to each of the prototypes of the different classes you've seen so far, and whatever is closest will be the prediction. So this has the nice advantage that the class mean will not deteriorate when new samples come in because it's not affected by new samples, only computed from the samples of the class. And at the same time, by this distance-based rule, all classes compete to each other. You do not have the effect as we had before that one is a binary classifier, another binary classifier, but they're not calibrated against each other. If you have a fixed feature representation, this is actually great because you can compute these mean vectors on the fly by just taking your old mean vector, scaling it appropriately, adding the new samples you have, rescaling it, and you have the exact new mean vector with respect to a fixed feature. So you can say that class incremental learning with a fixed feature representation is essentially done then. The problem comes in when you do want to learn the representation as well. So then the average vector across all images changes when your representation changes. You would have to recompute it after every update of the feature representation. And in order to recompute it, you need the training examples, and that means you have to store the training examples, and that would mean that you have to store all data you ever see, and this clearly is not scalable anymore. You cannot just do this. It doesn't fulfill the conditions we had in the beginning for being class incremental, because if we have to store all the data, we can just do anything anyway. So this is the position where we came in, and we thought about this is a nice concept, but can we make it actually class incremental without having to store all the data and without having to give up on a learned feature representation? And what we came up with is our proposal called iCaRL for incremental class and representation learning. It's a very simple, intuitive thing. So I will just give you the steps. And if you want the details, there's an archive paper online that has all the derivations and so on. But it's really not that hard to understand. So the main thing is we will still keep some kind of feature representation, think of a deep network. And in addition to that, we will also keep a certain small number of example images. So in actual image form. In order to make this practical, it will be bounded by some constant. So let's say at most 1,000 images we can store. And then we have to deal with the fact that, well, there is more training examples. We will have to do some selection of samples. We will still have some kind of output layer, but we will only use it for representation learning, not for classification. And for classification, we will do something very similar to the nearest class mean, but it's not the mean of the not the mean of the training examples, but just the mean of the exemplars. So let me go through the steps. The first thing is, how do you classify an example in our setting? So you will have an image X given, and you already internally have stored your set of exemplar images, one set of example images for each class you've seen so far. And of course, you have access to your internal feature function. And that what do you do? You compute for each class a prototype, which is the same as the nearest class mean, except it's only the average over all exemplars that we stored instead of over all training examples. And then you use the same rule as before. The image is classified as the class of the prototype that is closest to the current feature representation. And clearly, when the feature representation changes, you have to recompute this mean of exemplars, but you don't need all training data anymore. You only need your prototypes. So this is the same distance-based classification rule. So then, how does the training of, so this is the classification step, and you can see that at any time during the process of training, you will have a prototype set, so you can do multi-class classification, no matter how many classes you've seen so far. This rule is always applicable, right? It's like any time classification. So the main point is, of course, how do you train? So how does this system incorporate the classes one after the other? And it updates its representation, and it updates the prototypes. So it's an incremental training from every stage, every situation that you are. You get a new class batch, a new batch of classes, and you want to update yourself internally such that afterwards you're in a better state, and then you're ready for the next batch of classes to come in, and so on. So, as I said, first you will have to update your representation, so that's a step I'm going to talk about next. And then you will have to change the exemplars that you have, because if you see additional classes, then of course you also have to store exemplars for the additional classes. But if you're smart about it, then your storage will be completely full with exemplars already. You don't want to waste space. So first of all, you will have to compute how many exemplars can I still keep around per class. That's just the total number divided by the number of classes. And then afterwards, you will have to reduce some of the exemplar sets, and you can construct new exemplar sets for the new classes that came in. And then afterwards, you're done. You have a new representation. You have new exemplar sets. So you're updated, and you can wait for the next batch of classes to come in. So the representation learning is pretty standard, except we have two little twists on it. So given some kind of training examples of some kind of classes, we will first build a combined training set that combines all the training examples and all the exemplars. And then we have we train a loss function using any optimization you want. And this loss function has two parts. One is the classification loss, and one is the distillation loss. So let me show you what these are. So as you might have seen, the training set is all the training examples we have at the moment. Of course, we're going to use them. But then since we also have exemplars in storage, we're also going to use the exemplars, because why not use them? So ultimately what this means is we will always have a lot of new data, and we have a little bit of old data of all previous classes. So the system will be continuously reminded of what the old classes actually was. So this will prevent this catastrophic forgetting a little bit. The second step to prevent this forgetting is the loss function. So let me go into the steps. So there's two loss functions. One is evaluated for the new classes for which we do have training data, and one which is evaluated for the old classes for which we don't have training data. So for the new ones, we have proper labels, we have a lot of data, so we just have an ordinary cross-entropy classification term, just log loss. Right? The second term, the so-called distillation loss, it mirrors this distillation behavior by Hinton, where we first evaluate our network before training on all the new examples. We store these values, and then this distillation term will encourage the network to keep the values of before training around. So it will try to, the first term will make it learn the new classes, and the second term will make it not forget the outputs of what has happened before. So we don't have labels for the old classes anymore. We cannot train like classifier on them, but we still can say that whatever these previous outputs were, they should not change too much. So this acts as a regularization also in order to prevent forgetting. Okay, so that leaves how to manage the exemplars. So we need to be able to take an existing set of exemplars and reduce it in size, and we must be able to construct a new one. The reduction in size is actually very easy. So if we have a set of, I don't know, k exemplars already, but we can only afford to keep m of them, well, we just keep the first m in the list and throw away the remaining ones. Right? So that's an easy, I mean, you can execute that any time without having access to training data. You just reduce your set. In order for this to make sense, you need a routine to construct exemplar sets that is like robust against throwing away a certain number of them without breaking the good properties. So the construction of the exemplar set is actually designed such that no matter how many of your exemplars you use, you will always get an as good as possible approximation of the mean, which is the nearest class mean that we're going to approximate. So it's a procedure that reflects a little bit this herding idea where you do a greedy selection. You start with nothing and you choose one sample that is as close as to the mean of your training data as possible. Then you choose the next one such that the average of the two you now have is as close to the mean as possible. Then you choose a third one that is, when it's averaged with the ones you already have before, is now the result is as close as possible to the mean, and so on. So by construction, no matter how many you take, there will always be a good approximation of the mean. And that's what we need, because eventually later we'll throw some away. So, and we cannot retrain anything at that stage because the training data of those classes is already gone. Okay, so these are representation update, reducing the exemplar set, constructing a new exemplar set, and that means the training stage is completely controlled. So now let's see how it looks. How does it work? We did experiments on standard data sets. This is the CFAR data set with 60,000 examples, and we train a ResNet with 2,000 exemplars. We also did one on ImageNet, where we have 1.2 million training examples, and another ResNet, slightly more exemplars, so 20,000 exemplars for 1,000 classes. That's like 1.5% or so of the training data. And then we compare when the classes come in different batch sizes, like 2 at a time, 10 at a time, 50 at a time, how does the performance compare? And we have to compare to some baselines, of course. So one baseline is just ordinary stochastic gradient descent training without caring about catastrophic forgetting. Maybe that was just hallucinated. Maybe it's not a problem after all. One would be we first learn the first batch of classes, we can do everything, but then afterwards we fix the representation in order to prevent catastrophic forgetting. And one is a variant of the learning without forgetting by Lee and Hoyam earlier this year, where this distillation term is there to prevent forgetting, but it's not using any exemplars. So here are results, and as you can see, so this is for different situations. Blue is the accuracy that the iCaRL method finds, whereas the other curves are the other. So, I mean, visually it's clear that this is a much more nice and stable behavior. It's not surprising that it goes down. After all, on the left, it's a classifier with 10 classes to distinguish. On the right, it's 100. But what is kind of shocking is that all the other methods drop down so quickly, right? So similar in the ImageNet example, the blue curve stays quite nicely considering that it's more and more classes. But some of the others really deteriorate quickly. So just to give you an idea why that is the case, let's have a look at the confusion matrices. So these are the confusion matrices on one of the data sets. And you can see that our method, well, it's not perfect, but the mistakes it makes are more or less spread evenly. So sometimes it confuses one thing for another. But if you look at the others, you see very extreme effects. So for example, the fine-tuning, so if you just continue training, it will only predict, no matter what the true class is, it will always predict one of the last classes, because it has forgotten that the old ones even exist. The other way around, if you fix the representation, it will preferably predict one of the original classes for which the representation was fine-tuned, and it will do much worse on the later classes. And the distillation-based learning without forgetting has a certain bias towards later appearing classes as well. So that's my summary. I think the problem of class-incremental learning, it's so simple, it's so intuitive, but it's really far from solved. So I should have said that all of the plots I showed you are still clearly worse than if you would have the ability to throw all your data together and train, IID on everything. So it's still worse to train class incrementally than to train together. The iCaRL method, it shows that if you just keep a small number of exemplars around, your performance actually becomes much more stable and much better. And it's not surprising that additional information will help you, but the amount by which these few examples help really surprised us. And there's several open questions. In particular, are these exemplars, I mean, is it an outlier for this situation? Or maybe we should think more about keeping exemplars around also for other methods. And in the other direction, what if we cannot do that? Maybe there's some privacy issues and we cannot just store a bunch of images in our classifier. So is there alternative ways to overcome this problem as well? So let me thank my group, in particular Alex and Sylvester, who did that, funding sources, and I have time for a few questions, returning back to the summary slide.
Good questions? Pascal?
Since you're keeping exemplars around, did you consider doing a nearest neighbor instead of nearest mean?
So the original work by Thomas Menzing and others already did that. So the nearest neighbor was doing considerably worse at that time, possibly because it's a very high dimensional representation. If you have individual examples, there might be like hubs where everything is classified to. And I suppose that just the averaging effect helps in the stability. You can think of it also as like you approximate each distribution, a class conditional distribution, by just a Gaussian, and then you classify, you just say which Gaussian has the highest likelihood. So it's more a generative than a discriminative thing there.
Yeah, so you said that basically if you take all the training data, it should probably stay stable, right? It's almost 100%.
The curves?
Yeah, the curves.
No. It would still go down because on the left it was a 10 class classifier, and on the right it was...
Did you try it? Did you measure it?
We know that on the right-hand side, it's the normal numbers of CFAR and ImageNet, right? So we know that it's like 70%, whereas ours is like 50 or so, right? Yes. So,
okay, so you're saying even if you have all the data, it drops?
No, it clearly drops because on 100 classes, where CFAR these days close to 80, I guess, right? And then if you train 2 at a time, you drop down to 40. If you have just 2 steps, then you stay at 70. And of course, it depends on which classifier, which network, and so on.
Sure. And then another question, did you measure the impact of the number of exemplars or whatever additional training data you use? How many do you use now?
We actually, unfortunately, didn't. So we did, the paper has a lot of comparison of like which part of the loss has which impact and so on. What we didn't do yet is run it with different sizes of prototypes. It's very obvious that the more you take, the better it'll get, right? But we don't have it quantified yet, right? That comes next. Sorry? So we had 2,000 for CFAR and 20,000 for ImageNet. So that's, 50 megabytes or so if you store them in compressed form.
I have a question. What happens when the distribution of classes is not uniform?
What do you mean? So
well, you don't have the same number of, at the end of the day, you don't have the same number of examples per class.
Right.
In these examples, they are very uniform.
So yes,
it seems that the number of exemplars should vary, but you don't know the distribution until it happens. So.
What in the end, what this message more or less does is it stores the class conditional density distributions, right? So it's always appearance given class label. So if you have different balances between classes, you might want to just learn a class prior instead of putting more. If it's really diverse, maybe it's worth it. We haven't tried.
Okay, we're out of time, so let's thank the speaker again.